And we are live. And welcome to Clubhouse. I'm your host, Dan Miller. And we have Leon Simons joining us here in just a second here. Uh, just as we go live, 1 second, as I let uh, Leon in here. Hold on 1 second, Leon. Um, Leon will join us in a second. So anyway, welcome to Climate Chat. I'm your host, Dan Miller, and we have Leon Simons with us here, just joining at the beginning of the room here. And today we're going to be talking about climate scientist James Hansen's recent communication. It's not a peer-reviewed paper. This is like a memo that he writes about the previous paper, which was Global Warming is Accelerating. And Leon and I covered that here previously. But this update is the 2025 temperature update, which is interesting in its own right. And we're going to be talking about that. And in addition to that, we're going to be making a special announcement. Leon, are we ready for that now?
Sure.
So the special announcement, which you might glean from the title slide, if you took a look at that, is that Leon is going to be joining Climate Chat. It is joining Climate Chat as a host, and I don't want to use the word co-host because that would imply that he's going to be joining me on all these rooms. No, instead, Leon is going to be bringing additional content to Climate Chat and be doing his own, well, I call them rooms, I guess, from the Clubhouse days, his own programs and his own interviews. And I'll be joining him sometimes, and Leon will continue joining me sometimes. And it's going to, eventually probably double the amount of content being generated every week. And for those of you who follow Leon, you know he's very prolific already on Twitter and Blue Sky about publishing the latest science about temperatures. We're going to talk about some of that today. Actually, the post that you made today about 2025 sea surface temperatures. And so I think having Leon join us is going to be great for everyone because you're going to get more climate science, in-depth climate science, and you're going to get more content from Climate Chat every week. And all in all, I'm looking forward to it very much. Leon, welcome to Climate Chat.
Thank you very much. Thank you for having me on the team and to work together on bringing the climate science to a broader public. And I think what I really like about Climate Chat is that it provides an opportunity for scientists to really talk in depth about their research, right? Even at scientific conferences, scientists often have like 20 minutes or 10 minutes or maybe only a poster presentation to share their work even with colleagues. And what I really like about Climate Chat is that we provide the opportunity for scientists to talk about the work they know most about, right? You often see, indeed, in this time with Twitter and then with social media in general, you see a small aspects of the science, and then another scientist or another climate communicator says something opposite, and then the media just present it like those two opinions or statements are of equal value. Well, of course, the scientists who have been doing the work often, like research on a scientific paper, often for years, and of course, within their career, they have often been doing the research on the certain subject for decades, right? So they really know a lot about these subjects, and a sentence, whether it's on Twitter or whether it's in a media article, doesn't do all that invaluable work these scientists do. Doesn't do that justice. So that, I think, Climate Chat does provide an opportunity for real scientists to talk more about what the findings of their work are and how it compares to other work, but especially and also to raise the important questions, because you and I, we have quite in-depth knowledge in general about more general knowledge about the climate system, about politics, about energy system, and how things develop. Um, well, of course, what we don't have is a decade's worth of experience of a single subject, and I think it's with our expertise we can ask the real experts on certain subjects the important questions and build from there. And what I've seen is yeah, sometimes scientists really benefit from that as well to and build on their work, and also, for example, start thinking about maybe how their research can connect to other research, or how it can also um, benefit climate solutions. I think that's also really necessary, because that's yeah, it should really, at the time of rapid climate change, we really need also the climate science to be more and more policy relevant, because yeah, that's.
I agree. And we're going to, by the way, this is not the only change to Climate Chat. Over the next little while, we're going to be adding new features, including, by the way, YouTube memberships and Patreon. So if you want to support the other efforts we're making to expand our reach, you'll be able to do that, and you'll get special benefits for doing that, which we'll talk about, in the future. But we're also going to be upgrading the technical systems here to improve the quality of the video and that kind of thing, bring it more into sort of YouTube standards, I guess you want to call it that. And so we'll be working on those kinds of things too over the coming months as well. And so there's going to be a whole bunch of changes. And of course, we're going to continue with lots of interesting interviews in depth, as Leon was talking about, and not trying to sugarcoat things. I think that's one thing about Climate Chat that we're kind of famous for, is that we kind of tell it like it is, and we bring in important voices. And one of the most important voices in climate is James Hansen. And for those of you who really don't know who he is very much, he originally was studying Venus and the atmospheres of Venus when he had the chance to study the Earth, and he realized, oh, I can study a planet whose atmosphere is changing over time, and that was exciting for him. And so he started studying the Earth and climate change, and in 1988 he was a spoke to Congress about climate change and warned everyone back then that the climate was changing, that we would see the difference by the end of that century. And he made a bunch of other predictions, all of which, by the way, have come true. There is this denier meme that he got it all wrong. But actually, when you look at his paper, actually from 1981, I think it was 81 or 82, in Science magazine, where he laid it all out and made certain predictions using very rudimentary climate models. He gave sort of an A, B, and C scenario, because he didn't know how much greenhouse gases humans would continue to emit in the future. So he said high, medium, and low. They ended up following, we ended up following the medium B. And when you look at the temperature, he was like basically dead on predicting what the temperature would be, roughly today or recently. He's continued to study climate change. And the thing that I love about Jim is that he takes a systems view. He's taking all of the data. He's taking the models, the paleoclimate history, the physics, the common sense, and things like that. And he works with colleagues such as Leon, who was a co-author with Jim on his groundbreaking Global Warming and the Pipeline paper, and also got a special mention, like a whole paragraph mention in the recent Global Warming is Accelerating paper as well. So Leon's been an important contributor to Jim and doing important work on his own right. So that's what's happening. That's kind of the special announcement. So this is having Leon join us and expanding the scope of what we do here is step one, and we're going to continue, and probably also expanding to new platforms to have broader reach. Because really what our goal is here is to inform those who want to take the time to learn about climate change, to really empower them with the latest knowledge. And by doing that, you'll be able to influence others. So it's not like we're looking to get millions and millions of views ourselves here. but we want to empower those who are interested in understanding climate change in more depth, more than just the headlines that you read, to give you that information from right from the climate scientist's mouth. But we also, by the way, don't just cover climate science because, to be honest with you, to fight climate change, we really know all the climate science we need to know. We actually already know all about all the solutions we need, at least to get started. Uh, but we're not doing anything. We're obviously, as we talked about recently, we're moving backwards on all of that. And that's because we also don't have the right communications. There's humans have psychological issues where they ignore future problems. And so we also talk about communications, we talk about psychology, we talk about marketing and all these kinds of things, everything to do with climate change. And we'll continue to do that. In fact, next week we have David Fenton, a returning guest, who's an expert on how to communicate about climate. And so you're going to see more and more, as well as bringing in the scientists. So that's the announcement. I don't want to spend too much time on that, unless, Leon, you have a couple more words to say. And we should dig right in now to what Jim Hansen came out with. And I thought maybe we'll do it sort of the same way we did it last time. I did a super short summary. Now, his memo is only two or three pages. It's not a long memo. I forget how many pages it is actually, but what I do when he comes out with those is on Twitter and on Blue Sky. I do a super short summary, a too long didn't read kind of summary for people, and which I did for this one as well. And so I'll just go through that, spend a few minutes and highlight the major points. And then Leon can get into the details and also, by the way, expand beyond what Jim said because he has some updated temperature data and things like that. So the title of the memo is The Acid Test, Global Temperatures in 2025. And a link to the whole paper is in the video description on YouTube. And a lot of other links are there too. So if you want more in-depth information, you can go there anytime and grab that. So what Jim said is that the unprecedented jump of 0.4 Celsius in 2023 and 2024 was due to two basic things. Why did it jump that much? Which is a crazy amount, by the way, to jump in essentially a year. And that was due to two things. One, El Nino, and the La Nina, and there's an El Nino La Nina cycle that happens in the ocean water in the Central Pacific. When it's La Nina, it tends to cool the Earth a tenth or 2/10 of a degree. When it's El Nino, it tends to warm up a tenth of a degree, 2/10 of a degree. And so 2/10 of that 0.4, or half of it, is due to the switching from El Nino, La Nina to El Nino. And that was expected. We had like a 3-year La Nina, so it kept things cool for a while. And then it switched. And when that happens, and this is a natural cycle. Every few years it switches. So you kind of want to average that out. But right now that made the temperatures jump a bit. But that only explains half of it. The other half, Jim says, and Leon says as well, by the way, is that the extra warming, the extra 0.2, was due to a rule change by the International Maritime Organization that said that ships had to lower the sulfur content of their fuel by 80% starting in 2020. The original drop started in 2015, but the big drop went into effect in 2020. Now you might say, well, wait a second. If it happened in 2020, why didn't we see the big jump in 2020 rather than in 2023? And the reason for that is that there was a La Nina, a cooling phase that was offsetting the warming from the ships at that time. And then when it switched to a warming phase, it no longer, well, two things. It added the warmth from El Nino, and it was no longer hiding the warming from the ships, and we got the full 0.4 degrees. I should say that everything we're telling you about today, and what Jim is saying, is not universally agreed to by, let's call them, some mainstream climate scientists. There are some who say, yeah, that's amazing what happened, but we don't know why. And we've had them on our show, Michael Mann and Gavin Schmidt and others like that. who have said, yeah, something happened, but we don't know what it is. And Jim is saying, no, we do know what it is. And what's really interesting about this communication, well, there's actually a lot of things that are interesting, is he says that the temperatures in 2025 are going to tell us who's right. So if Jim is right and Leon's right, then 2025 will be a warm year. Maybe the warmest year, but just, if it's up around 2023, 2024 levels, then that would sort of prove the theory. And if it drops a lot and it's really a cold year overall, then it's probably something else. And it's not like other people have explained it, but it means it's probably something else. Okay, so that's what's happening. I think Leon will show you some of the graphs of the temperatures a little bit later, so I'm not going to do that here. And one of the other super important things besides the shifts, is that Jim is saying that the climate sensitivity, which is defined as how much will the Earth warm if you double CO2, and that's like, I want to make sure that's a scenario. It's like, if you do that, it's like a measure. For a doubling of CO2, you get this much warming. It doesn't mean, well, the thing is, we actually have doubled CO2 equivalents already. But you don't need to double CO2 to use ECS as a measure, is my point. And the IPCC typically assumes that's 3 degrees Celsius of warming for a doubling of CO2. And Jim says it's 4.8 C. And the interesting thing also in this communications, it explains that whatever the value is, when you make a new forcing, and a forcing is something that people do to change the climate, the thing that changes the climate. And then once you make, and that would be, for example, emitting more greenhouse gases, or all of a sudden getting rid of cooling aerosols. But then after that, the climate responds to that forcing with sometimes amplifying feedbacks. The amplifying feedbacks are not the forcing. So the fact that you get more water vapor in the atmosphere, water vapor is a greenhouse gas, but we didn't put the water vapor up there. So we did the greenhouse CO2, and let's say methane. And so the CO2 and the methane are the forcing, and the water vapor is the feedback. And Jim is making the point in this communication that the feedbacks take little time. So initially you get the warming just from the forcing, and then you get more warming later as the feedbacks kick in, and the feedbacks are due to the initial warming. So what Jim is saying is, if the IPCC is right and the climate sensitivity is 3 degrees, then the impact from the shipping change would be complete this year in 2025, or like be complete by 2025. So we shouldn't see 2025 being a warm year, because even if shipping did it, but ECS, or Earth climate sensitivity, is 3, then we're done. But if Jim is right and it's really 4.8, then there is more feedbacks to come, and they will keep happening based on that initial shipping change. And we're going to see a warm year in 2025. And so this is the year that will show who's right. The interesting thing is the map of the sea surface temperature that goes by time is indicating that Jim is right. So there's a lot more in it, but I want to turn it over to Leon to comment on what I've said already, and also to add to that. So Leon, all yours.
Yeah, thank you. Can I share my slides again?
Yeah, I think you can. You should just be able to do that. I'll tell you if I see it.
Yeah, thank you, Dan. I think that's a good summary, and I think it also helps to see the graphs. So I'll show them. And of course, we had a very long conversation after the paper came out. Global warming has accelerated. So I won't cover everything what we already discussed again in as much detail, but I think it's good to go over the main points Jim made here. And it is indeed, as you mentioned, the global surface air temperature, which is what many think of when they talk about or hear about global warming, right? This also this 1.5 limit, which we shouldn't cross. That's also part of also measured in this global surface air temperature increase. But also, as we already showed in our research over the past years, is that already the other signs, as the satellite data from NASA, but also the ocean heat content data, where about 90% of the heat from global warming goes to heat the oceans. That already shows a big increase in the rate. So faster, more heat is absorbed, less sunlight is reflected, and of the oceans are really the ocean heat content is really increasing very rapidly. So that's was already quite clear, of course, with the limited data, because since this IMO, the International Maritime Organization, clean air regulation came into effect, that was, of course, January 1st, 2020. And some other regulations before that, but the global impact was started on January 1st, 2020. And of course, now we only have, when we first published about this, we already, of course, mentioned this is, we don't have a lot of data yet because it's just a few years. But already we can see a strong change in how much sunlight is reflected back to space. And this is an important indication that the effect might be stronger than most assume, based on models, which of course have a lot of assumptions underneath them as well. And then and also why because this, especially because it has a lot of impacts, potential impacts, where many of us live, and on the AMOC and on extreme weather, that's also a reason to, even without sufficient data, because of course it would be better to wait 20 years and look back and to be more certain. But it was because of these impacts, it was already important to highlight what we are already seeing, and also the importance to keep measuring what's happening, right? To keep, maybe we need to more satellite launches of these NASA series satellite observation systems to make sure that we have enough data in the coming years to observe these rapid changes. So I think that's important to note. And then now, as we predicted during El Nino, already we predicted it back in 2022 and at the start of 2023, that when La Nina, because we had about 3 years with the tropical Pacific oceans were relatively cooling things down, or especially in the tropics. And that was also keeping a lid on the global temperatures, like the global average temperatures. And we already mentioned there that at the time before the El Nino started in 2023, that if the El Nino would start, then we would likely see very strong increase in temperatures. And of course, that's exactly what happened. And I'll get to that now. Let me share the slides. Share. Yeah. So the acid test, and of course, the acid test is like a proof of a theory, right? But it's also, of course, in a way, a funny wordplay, because the sulfur emissions, of course, from shipping, of course, were cause acid rain and make the oceans more acidic. And as Dan mentioned, Jim worked on the planet Venus, which has a lot of sulfur on it. So it's yeah, I think Jim has a really nice way with words. And yeah, so in a way, it's like not really a prediction, but an explanation about what if 2023 will be. It could be again maybe as warm as 24, maybe even warmer. And then why is that? Right? So starting with the sulfur. So this is the global sulfur dioxide emissions uh, around the world. So of course you can really see clearly where all the industry is happening. This was in 2010, but also the oceans, there was a lot of sulfur being emitted. And the IPCC already presented that until about, I think that's 2014 to 2020, sulfur dioxide emissions were causing a cooling of about half a degree, but maybe almost as much as 1 degree of cooling up to that date. Because it was indeed, again, reflecting sunlight back space, but also making clouds brighter, and then masking part of the warming effect from greenhouse gases, because greenhouse gases cause up to that time about 1 to 2 degrees Celsius of warming already. So without these sulfur emissions, and Jim calls it the Faustian bargain, like a deal with the devil, where you get all the very cheap, clean, very cheap energy, but you don't get the impacts of global warming because the sulfur is masking it. Because sulfur is it's almost like a mythology, right? With the devil and all the sulfur that comes from the ground. But this is real science. This is real. Like this the also the IPCC consensus is that these sulfur emissions have been cooling the planet quite a bit. So what happened now? So you can take this sulfur, because the sulfur is already in the fuels when you take it out of the ground, and if you burn it, it will end up in the atmosphere. But you can take it, you can use hydrofracking. So you can use hydrogen to take the sulfur out of the fuel, and then you can store it. Like they were building these enormous pyramids in Canada and Alberta, where they take this from these oil sands. They take out the oil, but then they take out also part of the sulfur that's in there and then they just store it there and build these enormous mountains of sulfur. And that just has been scaled up because of these clean air regulations. The desulfurization has been scaled up, so more sulfur is taking out of the oil.
I think by the way, it's worth mentioning that sulfur in the atmosphere is bad for you. Burning fossil fuels releases sulfur and other particulates. And there's a Harvard medical study that shows that they attribute 8 million deaths a year to the burning of fossil fuels. That's 1 in every 5 deaths. So this is bad stuff when it's in the troposphere or the lower atmosphere where we breathe it in. And so there were reasons why the International Maritime Organization and other organizations are working to get rid of the sulfur because it's bad for your health. It just so happens that when you do that, there are other impacts as well.
Yes, and that's also indeed why they started to limit the emissions closer to the coasts, for example. And of course, they started also with industry, where they desulfurized the coal plants. So they cleaned the emissions from the coal plants. It was also impacting statues, so causing this acid rain, and it all these environmental and health impacts. And again, it also worth mentioning that these deaths are not just from sulfur emissions, but also from other pollutants that are associated with the burning of fossil fuels. And nature also produces sulfur it emits it from volcanoes, but algae and other plants also emit sulfur. So it's also natural. So it is quite hard to assess the health impacts. As someone who has done a lot of research in Ethiopia, where we spent half a year with women who were working in these bakeries with backpacks, where they had these air filter systems, and doing research on their health impacts of using biomass for cooking. It's really even it's very clear what the exposure is, and it's still quite complex to assess the health impacts, let alone from all these other co-pollutants and all the other impacts, right? So there's a big uncertainty also what the health impacts is, and yeah, so I think that's also an important disclaimer, and that's not to downplay the health impacts, of course, but it's yeah, there's uncertainty both in the climate impacts and in the health impacts of these pollutants. Okay, and then as we discussed in detail last year, last I think 2 weeks ago, when we talked last time when we discussed a new paper by James Hansen and colleagues on climate change. We discussed it in detail, but where you can really see in this the northern hemisphere mid latitudes where most of the sulfur was being emitted by ships, about half of all sulfur emissions from shipping happened between 20 and 60 degrees latitude. And you can really see, especially over the higher latitudes, that there's a lot more the sea surface temperatures they are rapidly warming, and Makiko, also a close colleague of James Hansen and myself, she calls this a northern hemisphere mid-latitude El Nino, a permanent one. So, and then of course, this is where we produce our food, where we live. So this is also where it will have the most impact, and this is not going away. You see here the El Nino, this is the tropics. So the sea surface temperatures in the tropics spiked, of course, during the El Nino, but now they are again decreasing. They are now from dark red, they went to red, and probably will go back to brown. But this this has reached a point of over 1.6 degrees Celsius at certain latitudes. It's the 12-month running average sea surface temperature anomaly. And you can really see that there's enormous continuous increase over this region. And there will likely only increase because there's still a big imbalance, an increase in the imbalance. So more heat is accumulating faster, and this will take a while to materialize further. And
by the way, let's go back to that because I think it's such an important. This is such an important graph, and yet it's a very unusual graph. People haven't really seen this before, so they don't even understand what it is. So let's just talk a little bit about that again. So at the bottom, you have time. So starting in 2000, and the last points are the beginning of 2025. Well, actually, or right before that, actually. And then you have the latitude. So what this is sea surface temperature, so only the oceans. And what it is every point, like at 30 degrees north, this would be the average temperature of the entire ocean at 30 degrees. And it's not the temperature itself, it's the anomaly. So it's how much it's changed from some reference period. So of course, in the Arctic, it's colder than in the equator, and the Antarctic is colder. But all that's sort of removed because we're talking about the change from the reference period, which I'm not even sure what the reference period here is. So that's why, as you see it going from left to right, all the colors are getting darker and darker because it's getting warm. The whole world is getting warmer. The oceans are getting warmer, but we can see these areas where something unusual is happening, and that is starting in 2020. The oceans, basically the North Atlantic and North Pacific oceans, were getting warmer and warmer and warmer. And I wanted to point out something you were pointing to here. This little dot right there, that if you look at the bottom, that so it goes red, very dark red, and then it goes to this pink after it gets 1.6 degrees anomaly. And we can see that just beginning here. So this you can tell is getting warmer and warmer. It's not dying out like an El Nino dies out after a little while. And these are La Ninas here, as you pointed out. So
yeah,
this graph is a super important graph for understanding what's happening to global warming acceleration. And
Yeah, and
what I
also
don't understand, yeah, go ahead.
yeah, it's important indeed to also this really clearly shows that it's not global warming only. It's also very much regional warming. And when we discuss acceleration, when we talked about that in the past years, were very much talking first about this region where we saw, of course, the decrease in sulfur emissions having the most impact first on in the satellite data and then on the sea surface temperatures, which just kept increasing even more than I think at least than I thought would happen in such a short period of time, right? Because it's such an increase. It's about half a degree of warming, or even more than half a degree of warming. It's if you look at the longer historical data from ships taking measurements, we see about in this region that there's been more warming in the past 15 years than in the preceding 150, and that's really, I think, mind-boggling. But let me get to the global because
And
I think
but if you even take this point in 2020, you see the light brown, you go down there, that's uh, zero point 0.8, I guess, right at the border. And now we're at 1.6. That's zero point 0.8 C of warming in 4 years, 4 or 5 years. That's crazy.
yeah.
Anyway, yeah, let's keep going. But I thought this graph is just so important. It's worth spending time to help people understand what's going on there because it just looks like blobs of color if you don't have
Yeah,
it
I think it
explained.
helps it helps for people to indeed to try to grasp what it says.
But
I think
I would say one other thing. This graph, if you're going to disagree with Jim Hansen and with Leon about ships and whatever it is, you still have to explain this data. This is data. This is not a model, of the future. This is data based on what's already happening with measurements happening by these Argo floats in the ocean and things like that. So if you're going to disagree, that's fine. Great, great. What's your alternative theory that explains what we are seeing? And I haven't seen that from anyone who's
yeah, I would
disagreed.
love to have an alternative explanation, which also tells us that this will rapidly start decreasing soon, and I hope that they will be right. But indeed, like many of the criticism has only been about yeah, it's been a lot of strawman arguments and ad hominems rather than indeed address the data, we would love to have the conversation about the data. But yeah, that's of course I think that's maybe part of the part of it, and I think there's a lot of denial because I think people don't want this to be true as well, right? But let me continue, and then we can discuss further later. Um, so this is also part of the update by James Hansen, and what it shows here is that if you look at the 1970 to 2010 trend, there was about 18 degrees Celsius per decade, and then if you look at the from 2010 to now to present, the trend is 0.36 degrees Celsius per decade. So that's a doubling in the rate in this increase in surface air temperatures. And I think that's not really surprising because also already in 2021, NASA and NOAA said that the rate of global heat uptake had doubled. So I think it's not surprising. It shouldn't be surprising if you look at that data and you see that the trend has even increased further from since then, the heat uptake. Then you would expect that will translate to a more or less a doubling in the rate of surface warming as well, which is what we see now. Was again with would be nice to have more data, but we already see that we are more or less in the range of 1.5 degrees Celsius of warming, and this uses NASA GIS temperature data and that's a trend from 1880 to 1920, which they use, which James Hansen has been using for a long time as a reference period of the pre-industrial, based on the available data within the data set. That's important.
By the way,
Um,
before we go on, because it is important for aerosols, I think it's important to point out what's been going on since 1880 until about 1970 when the temperature started going up at a steady rate. And that is um, global warming is determined by the cumulative emissions of CO2, not by the yearly emissions. And so even though yearly emissions in 1880, might have been pretty significant, not compared to today, but still significant, um, it just didn't have it didn't the total amount in the atmosphere hadn't changed very much yet. But what
hmm.
did change then is the smoke, the aerosols that were released from all those coal plants that didn't
Yeah.
have sulfur scrubbers on them back then, by the way. And so,
Yeah, so but indeed, so around 1980, there were over 100 million tons of sulfur being emitted every day, and that was more or less continuous emissions.
mhm,
Um, and now in the Netherlands, at least, we are sulfur emissions in most of Europe, especially Western Europe. Sulfur emissions are below their levels, their emissions in 1900. So
mhm.
we are really, and that's possible because because of what's called desulfurization systems. Last week I was at a coal plant in a coal-fired power plant, the largest one in the Netherlands. It's in the Eemshaven in the north of the country, to see. I call the baseline. So what's happening now? How do we produce electricity? And they burn there 80 million tons of coal. And that's a very large ship. It's called Panamax ship every week. They also burn biomass, but mainly coal. And of course, that would emit a lot of sulfur if you burn 80,000 tons of coal every day. Of course, that produces a lot of CO2, over 5 million tons of CO2 in a year. But it also there's a lot of sulfur in there as well. But what they do is they use these desulfurization systems where they use chalk, and they have this enormous like shower heads where they and they 5 megawatts worth of pumps for every coal boil, and they rinse the sulfur from the exhaust gases, and that reacts the sulfur reacts with the chalk and becomes gypsum, and that gypsum is sold on the market. And with that, so they don't emit sulfur anymore, but they do continue to emit a lot of CO2.
Of
And
course, yeah.
that's, they invested 4 billion euro in that coal plant, and there's many of similar, of course, still coal plants built around the world, and those plants are often built for with a visual lifetime of 30 years. So that's also when we talk about global warming in the pipeline, we also talk about these emissions in the pipeline, right? Because you have to take that into account. We won't stop or industry or the world is not planning in practice to stop burning for fossil fuels overnight. And that thing that's important to take into account. But
So wait,
let me
let
give
me
you.
just finish. Wait, go back one. I just wanted to finish what I was saying here. So in the beginning of the Industrial Revolution, the aerosol cooling was stronger than the greenhouse gas warming. Again, greenhouse gas warming is a cumulative thing, but the aerosols, they only last for about a week in the atmosphere. So it's the amount you're doing that week. And that was growing rapidly and caused actually cooling. We got here, and then there was World War II. After the war, we rapidly industrialized, a lot more aerosol emissions happening faster than the CO2 was accumulating in the atmosphere, and there was sort of a steady, warming. There was no warming. And then the
Cooling,
1970s,
especially over the northern hemisphere, there, and in certain countries there was cooling.
yeah. And then 1970s, we passed the Clean Air Act, and other countries did similar things, started doing sulfur scrubbing in the United States for reducing acid rain, and with all the cleaning up of all the pollution, which was cooling the earth, we then saw a steady
Yeah, it
rise.
was masking the greenhouse gas warming.
Right. And that's why this is a funny graph like that. And we're just did a little more unmasking of aerosols, and therefore we're seeing this acceleration as well. Anyway, that's
Yeah.
an important graph.
Yeah, and then we can go into the specifics of China and India, which continue to industrialize, of course, and then also installed desulfurization system, especially in China and India now starting. But indeed, it's important to take those drivers into account, not just greenhouse gas, but all. If you really want to understand global, but especially regional changes, you really have to take into account these effects. And so the past 20 months. Depends a bit on the data set on how much warmer it was, but the past 20 months up to January, so from June to January, they all these months were above any preceding record. So any year, so in gray here, there's also again from the update from James Hansen. In gray, you see the temperature records before 2023. And then you see that from 2023 to 2025, now the past 20 months have all been above any previous monthly record in between 1818 and 1920. And that's probably, of course, a month. What is a month? You can discuss about that, but it's probably now warmer than at any time in the past 120,000 years, as far as we can determine from ocean data and from other that's called paleoclimatology, from paleoclimate data.
Also, just let's also just focus here. The difference between this graph and that one with all the color splotches. This is global surface temperature, not sea surface temperature. So global surface temperature includes the temperature around the globe, both over land and over oceans. And when we talk about global warming of 1.5 C, we are talking about global surface temperature. By the way, I think it's technically defined as 2 meters above the surface. So 6 feet above the surface is the measuring point for global surface temperature.
Yeah.
And so there you go. So I just want to make that clear. So because you know we're very used to it, but I think some people are looking at these graphs for the first time, and it's really good to put a reference on them.
Yeah. Sorry. And so this indeed, and then I think this month. So this was again if you see these months, and I'll get to that later. These were record temperatures. This of course was already quite a spike, but we didn't hit that in 2024. But I think it will be likely we will hit it now. We will hit below February. The February record, which was broken during the super El Nino of 2016, and the impact of this super El Nino, that really the strongest impact of that is in the February March, which you can also see why this spike is there. And now we don't have an El Nino, but I think Jim called a weak or not such a strong La Nina, but I think it might be. I think it might be. You know, it depends on how you look at it, but it might be quite weak still if you take into account the rest of the world. It's relative. It's if you look at the relative data, but I'll get to that. And this is again updated on I think up to yesterday. This is the daily sea surface temperatures without the Arctic and the Antarctic region, so global, more or less global. And then you see that again, the 2025 temperature without the El Nino is almost as high as during the 2024 when there was an El Nino. And I think that's one clear indication that things are not cooling down as much as we would like them to. And this is El Nino. Oh, sorry, this is the El Nino region. sorry, where is it? I'll get to it here. I thought I had it here, but I don't see the graph. So that's the tropical Pacific. In the tropical Pacific, you see now that there was a strong La Nina, or at least the temperatures similar. So that's also what NOAA declared a La Nina, where there was a cold tropical temperatures. But this was last year, 2024, when you see that is the average over time. And then you see that in this tropical Pacific region, which is used to quantify whether there's an El Nino or not. Well, it was really much warmer in 2024 than in 2025, and of course, it takes a while for this to translate into the surface temperatures. There's about a delay. If you have an El Nino peak, then about 2 or 3 months later, you'll see a global surface air temperature peak. So that was what is impacting the thing. This is the on the top you see that was 2016. That was impacting the temperatures, of course, in February, March, and this La Nina will impact, of course, the temperatures in February, March of this year, which are less hot than they would have been with an El Nino, I think, and that's. Here I show you the relative since 1950. I think it's a bit too much to go into now into all the details, but if you see the relative index, the relative Oceanino index, it shows that it's about 1.1 degrees Celsius, 1.1 below. That's the average of 3 months for November, December, January, and if you look at the El Nino, that was impacting January, February, March 2016. That was really strong. That was so that's the difference in how El Nino impacts of course the global temperatures. And here I show you that together. In purple, you see 2015 to 2017. The monthly temperature data is from ECMWF, and then in the dashed line, that's the relative ocean El Nino index. You see that the El Nino was much stronger than last year. So the El Nino we had in 2023 wasn't very strong, but still we had very high temperatures, right? And then also they didn't decrease very much. If you see the purple line here, it decreased a lot after the enormous spike. And now I also added the estimate of February 2025. I think it will be between 1.5 and 1.6. So it will be a bit colder than February 2016. But still, and I think that's the first time in 20 months we won't have a monthly record breaking. But the trend is still, if you compare it, if you look at the decade, so it's 0.34 degrees Celsius warmer than 8 years ago, average over these 21 months. And that indicates a warming rate of 0.42 degrees Celsius per decade, which is even higher than what James Hansen showed at 0.36. So it might be even higher than, if you look at it this way, it might be even higher than what we can see from the decadal changes. And why is that? I think, yeah, I can go into that in detail if you like, or if you want to. Would you like to discuss this further, or Dan?
Well, whatever. Yeah, well, you said this was like one of the most important graphs, so probably you should talk about it a little bit for those who didn't see it on Twitter or Blue Sky.
So I think this is one of the most important and shocking graphs I've made in quite a while, maybe ever, and it shows a lot. And I'll dive into it more detail. But what I do here is I compare the NASA series Earth's energy imbalance increase. So how much in the past, so there's data from 2000 to 2024, now up to December, of these satellites making observations about how much sunlight comes in, how much sunlight is reflected back to space, but also how much long-wave radiation, how much infrared radiation Earth sends out. And that's connected to the ocean heat content data, and then that's used to assess the trend. So how and then there's monthly data coming available to show, okay, how every month how has this changed, how have these values changed, and they give absolute values there. And then you can look at this data and you can look at how it changed from the first 4 years. This is a 48-month average trend where you just take the first 4 years and you look at how this data changes over time. And I take 4 years because then there's less variability from El Nino, for example, or from other effects. And then you see that really there's a big increase. But what I also show is what happens with different feedbacks. And I think it helps to take a step back because, and this is also what Jim talked about forcings and feedbacks, right? So climate forcings, it's what forces the climate to change. And that's of course greenhouse gases and aerosols are the main human caused, or what we call anthropogenic forcings. But what's also important is how the Earth system responds to these forcings, and that's through feedbacks. And the IPCC climate sensitivity estimate is that there's about 3 degrees Celsius warming for doubling of CO2. And that's a result of feedbacks. And for now, I think it's I'll dive into it later also on my website on Patreon. I'll dive into all these different aspects. But I think first it will help to look at the total effect. And what I use here is the like a very strong feedback, so very negative, and then the best estimate, and then a very weak feedback. And I will show you what impact that has using a different feedback. So these are the best estimates. This is the best estimate of the IPCC, and these are the ranges.
Yeah, let's talk about one of them though, because I think people won't know what Planck feedback is, although it actually turns out.
Yeah, I'll get to that. I think.
Oh, you are gonna.
Yeah,
okay.
I'll get to that, but
that's very important.
I won't just focus on this, but I think it's So I think to answer all the questions this raises, I think that will demand quite a longer discussion. But so what I did was first you have this change in global temperature, and this is again the NASA data, and you see that then in 20 years, first it again the 4-year average, there was a slow increase from 2024 up to about 2015. And then, of course, the warming accelerated after that, where you can see really these jumps. And of course, after the El Nino, it stabilized a bit. But now again, with the El Nino, you can see that there's warming is increasing. And I think with the next 4 years, we will see a big increase here. With the next years, there will be, so the next 4-year average, right? With another 2 years of data, we'll show this increasing much further. But what you can do then, if you have the global temperature changes, you can multiply this with the feedbacks. Of course, as Dan already mentioned, as Jim mentioned in his paper, some feedbacks take longer to come into effect than others. But this is just to explain what forces are at play here. Not just forcings, but also feedbacks, and then you can compare that to the data, to the observation data, and then you can, if you multiply these different feedbacks by the change in temperature, these will mirror the temperature increase, because so in watts per square meter, that means that for example, if it would be 1. If the feedback, which is for every degree Celsius of warming, the total feedbacks respond by causing more warming or causing more cooling, and the net effect of that, there's different values for that. But if it would be 1, so for every degree Celsius of warming, the feedback would be -1, then there will be a perfect mirror, because 1 multiplied by -1 is -1, right? So then this graph would be a perfect mirror of the feedbacks would be a perfect mirror of the temperature trend. But if you have strong feedbacks, more negative, then the more Earth warms, the more it will try to cool down, let's say it. And then the weaker the net feedbacks are, the less Earth will try to cool down from this forcing change. So that's forcings, but of course we also have that's feedbacks, but of course we also have the forcings. And that's these in purple. I show you the 4-year average climate forcing, and that's a total that includes the sun, the cycle, the 11-year cycle of the sun. That includes the volcanoes. But that also includes all the greenhouse gases, which have been increasing in the atmosphere, and land use. It includes everything. And then you see, this is also because the forcing first was negative, and that's because in the first 4 years, the sun was more active than in the years after that. And that will help to decrease this value. But then, of course, greenhouse gas emissions kept increasing, and that caused a positive forcing of over 1 watt per square meter over this period. And then what you can do next is add these two up. So you add up the forcing and the feedbacks. So that's how much how the Earth system responds, and how the climate forcings we've added to the system, and of course including the natural force. And then you can see that if the feedback is weak, that will cause a more increase in the positive effect from these greenhouse gas and the other forcings will be more visible. So that would have a stronger impact on the Earth's energy imbalance, right? Because it's relative to this period, and then you should see if and that also means the climate sensitivity is very high. That would show stronger impact, and if it's weak, then Earth's energy imbalance wouldn't have increased.
So let me try to I could ask it as a question to you, but to help people understand something, because it sounds counterintuitive. When we think about feedbacks, we think of the amplifying feedbacks. We think of more water vapor in the atmosphere due to warming from CO2, and that makes the planet even hotter. We think of melting ice in the Arctic or something, which exposes dark ocean that absorb more sunlight. Those are amplifying feedbacks. But there is one big feedback that you had on your chart but didn't explain yet. It's called the Planck feedback. And I'm going to tell people what it is, because I thought you were about to do that.
It's here.
Planck feedback is, as we warm the Earth radiates more energy out into space because it is hotter. But the thing is, the amount of energy it radiates goes to the 4th power of the temperature. So T to the 4th. In fact, I remember from my astronomy class in college, luminosity of a star equals 4 pi r squared sigma T to the 4th. And that's the same for the Earth. So this is
or anything,
or anything, but it's like the most important feedback. It's never talked about because it's just it's just part of the natural equation, I guess, of what happened. We always talk about those other heating
it's called amplifying feedbacks. Yeah.
This is the main negative feedback. So as
it's the main feedback hotter, overall. Yeah.
as the Earth gets warmer, what's supposed to happen is the Earth wants to be in energy balance, where the amount of energy coming in is the same as the amount going out. If we put some greenhouse gases in the atmosphere and do nothing and just do it for a while and stop, then there'll be a bigger blanket around the Earth. The Earth will get warmer, radiate more energy out into space, and finally find that place where the amount of energy going in is the same as the energy going out. And then the Earth would be a little bit warmer, and that would be it, and that it would stop getting warmer. But that's not what we're doing. We're continuing to pump more and more greenhouse gases into the atmosphere. And so that Earth energy imbalance, which is equivalent to about 1 million Hiroshima atomic bombs going off every single day, that's how much extra heat's coming in and going out. The Earth is still getting warmer. And as it gets warmer, that Planck T to the fourth is radiating more and more energy out into space. And even though we keep adding the blanket around with more greenhouse gases. So that's why this seems counterintuitive. You say, well, wait, the feedbacks are weak. It means high climate sensitivity, but that's because this Planck feedback, this T to the fourth feedback, is the dominant one. And those other
Yeah. So
amplifying
what that means, I think that's
feedbacks make it weaker overall.
and what that means, of course, you see the Planck feedback. There's very little uncertainty. This black bar shows the uncertainty. So the Planck feedback is about minus 3.22 watts per square meter of indeed negative cooling feedback for every degree Celsius of warming. So there's quite a lot of certainty about how this system responds, because it's just a physical response from, and of course, Earth's complex is not just a black rock in space. The moon is more easy, so if you use it for the moon, the certainty will be less large. But there's still, but the main uncertainty here is from clouds. That's what happens to clouds when the Earth heats up, and we've discussed it already in quite some detail. And I think we'll do that again in the future. But what that means that so going back to this graph where I showed these, so there's four things added to these feedbacks, and where then if the feedbacks is weak feedbacks, that means that that means also that probably the cloud effect is strong, and so for albedo, so more sea ice changes, for example, and less clouds causing more absorption of heat. So that causes this red line to be higher than the blue line, which would even though it says weak feedback. So it's a bit indeed counterintuitive. But then looking at the data, comparing this to the data, the NASA Sirius satellite data, it's higher than any of these other graphs, other lines on the graph. And I think that's quite worrying, that Earth's energy imbalance over the past 20 years has increased, looking at this data, by about 1 watt per square meter. And that's really an enormous increase in how much heat is accumulating on the planet. And that's on top of what it already was. Because I start here at 0, but that doesn't mean it was 0. It was about 0.4. So that adds, of course, that's why global warming has accelerated. And that means, sorry.
I just want to make a point here. And I understand why you're doing this. You're lumping all of the IPCC feedbacks together and saying, are they weak, medium, or strong? But the fact of the matter, as you're saying, is that each of them have their own uncertainty and dynamics, right? And things could be even worse than what's shown here if the negative feedbacks, the damping feedbacks are weak, and the amplifying feedbacks are strong, right? So
that's what this line shows.
Yeah.
It could be even worse. That's right. This is the uncertainty range, but there's an uncertainty range, and I think as you mentioned before, there's a tail risk, or so. But that's also what this line shows, right? This line is higher than their very likely range, so it's higher than the worst case scenario. So Of course, it's important to look at what causes this. And I think I'll do that in the future, and I'm already writing about this, where I look at also at the different, for example, at long wave impacts and at the short wave. So, and then you can start to look at what causes these changes as well. I think that's important, but I think this is and let me go to
Do you
this.
have the ECS graph from the communication? I have it right here if you don't have it. The one that shows the logarithmic scale of time and the different
Yes,
climate sensitivities of 2.6 to
yes.
4.5. Yeah. So I think it's worth, this is, by the way, I've been studying climate change for, over 20 years, but every time I read something from Jim, I always go, oh, yeah, sure. That's a good way to think about it or something, or some nuance that I hadn't thought about before. But when we talk about climate sensitivity, I think most of us think, boy, if it's 4.5 instead of 3, then as soon as we emit some CO2, boom, it's going to be that much hotter right away. And Jim says, no, that's not the way it works. Is that at the beginning, and you can see from this is like the sensitivity to some emission of CO2 or doubling CO2 all of a sudden. At first, the first 5 years, you don't even notice any difference because all of the warming comes directly from the forcing. The feedbacks haven't kicked in, the extra water vapor, the ice melting, all that kind of stuff. But over time, you see if the sensitivity is 4.5 instead of 3.4 in this case, or 2.6, it gets stronger and stronger over time. But look, this is a logarithmic graph. So as Jim puts it, you see the first third of the impact from your emissions in the first 10 years. You see the second third of the impact from your emissions in the next 100 years. And then you see the final impact from your emissions in the next 1,000, or actually looks like more like 2,000 or 3,000 years. And so that's what's happening here. And that's why he's also saying we'll find out in 2025 whether who's right about global warming, because at the first 5 years or so, if it was if ship emissions didn't really have this impact, or I'm sorry, if ECS was 3, it would be in here, and then we would be in this period. But he's saying no, it's going to keep going up like this.
That's the difference.
And we're going to see more of the feedbacks kicking in from that initial change in warming due to the ships. Because if it is 4.8, as Jim says, there's more in the pipeline coming, even in the first 10 years. So Leon, I have a question for you, which I'm going to ask Jim when we have him on the show. I've been, by the way, working with Jim to find a time to do this special interview we're going to do with him. It sounds like it's going to be pretty soon, but he's just wanted to get this communication out. He has some other personal stuff he's working on, and we're going to do the interview. One of the questions I'm going to ask him, ask you. We hear from a lot of mainstream climate scientists, one of the very hopeful messages is that if we cut our emissions to 0 tomorrow or 2050, or pick your day, whenever we get to net 0, then the world will stop warming. And the reason is that even though there's warming in the pipeline, the oceans will continue to take up CO2, just like they did the day before you cut down to 0 emissions, because the oceans only know about the total amount of CO2. They don't know about your yearly amount, and the total amount is totally out of whack. So they will continue to absorb CO2. And then there's aerosols are countered by the fact that methane will degrade to 0 over 15 years if you don't emit any more. So those 4 things cancel to get to us to a 0 temperature. But if ECS, or the Earth climate sensitivity, is really 4.8 instead of 3, does that simple math still work? Have you thought about that question?
Yeah, I don't think it does. But then, of course,
you don't think it, in other words, we will continue to warm another degree or so more than people thought once we get to net 0.
It's always it's a big if, and I think it's often indeed it's used as some hopeful message often, like when we stop emitting greenhouse gases, global warming will stop. But when is that, right? If that was 50 years ago, the answer will be very different than if it happens 50 years from now, when
More
we are
feedback,
in a
sure.
much warmer climate and when greenhouse gas concentrations are much higher. And so it's personally, I don't really like that way of thinking of the complex Earth system, where you just say, okay, if you would stop, one would stop, and then so that's hopeful. So let's do that, right? It's you know, if we're discussing the science, the answer is much more complex. It's maybe there will be less warm. Of course, there will be less warm. We need to reduce greenhouse
We
gas
need to get to zero
as
anyway.
possible.
Yeah.
But then warming will increase very rapidly in the regions where aerosol emissions were high. So maybe global average surface temperatures will not increase, or only half a degree, but India will get 10 degrees Celsius warmer, or the AMOC will stop.
No, the AMOX, that
And
throws everything off. Yeah.
we won't have a lot of extra warming, but sea levels will keep rising by 20 meters, right? So, that, for me, living in the Netherlands, I think that's more important than this global average surface temperature increasing by half a degree or not in the instant human extinction scenario, right? I think because it's just a hypothetical question, which right.
It's a scenario.
Yeah, it's a
It's a
scenario.
scenario. People think it's a prediction. It's not. It's a, hey, if you do this, then that. I do think, however, that this is almost a meme, that if we cut our emissions to zero, the Earth will stop getting warmer. By the way, Jim Hansen would 100% agree that cutting your emissions to zero is a good thing, okay? And it will have tremendous benefits if we do that. No end of story.
Yeah, it
But
depends how you reach that, of course.
well, I guess. And by the way, we might cut our emissions dramatically in the next few years because of the unintentional consequences of collapsing the economy. It'll be an interesting climate experiment if we do that, but it won't be pleasant for anyone if that happens. But no, but I want to say is that the idea that things stop getting worse once we hit net zero, I think lets a lot of people be encouraged by an emissions-only emissions reduction only approach to climate change. And they say we don't need carbon capture, we don't need solar radiation management, because if we can just get to zero emissions, and they think those other two things slow down the emissions reduction, but again, that's up to us if we're going to let that happen or not.
That's all these hypotheticals stacked on other hypotheticals, and what are we even talking about, right? I like to talk about the real world, where we see acceleration in warming, especially in regions where many of us live, try to grow our food, where we try to protect our country from ending up below the sea. And then that's what we need to focus on. We need to focus on what's happening in the real world, where we're not going to net zero overnight, right? And that's where we have to adapt to, and indeed, eventually, also is to start trying to make things from getting worse. Mm-hmm. And I think that's really crucial to take into account. And it takes a while for the scientific community to start including this data, where I try to I'd like to finish the presentation in a bit.
Okay, go ahead. And then I want to get to the end points that Jim made in this thing about why we care about accelerating warming and the political sector.
And I think that's also really what this relates to, because so I got some feedback from. You can see it, right? The graph. Yeah.
Yes.
So I got some feedback of my relatively simple graph, where I compare this NASA series data to the observations. And someone asked Gavin Schmidt what he thought about it. and he said that it doesn't agree with models, but I think that was a very surprising comment from him to make, because it really does, and it shows from his own research that it does. And this is the graph from Gavin Schmidt, where he showed, and I added some context, where he showed these climate models, and then the NASA.
Well, why don't you define your axes here? Not everyone knows SW,
I'm going. So
yeah.
This is shortwave and long wave, top of the atmosphere, all sky trends in climate models, which are all these dots, and this is the NASA satellite data. And this is the long wave, also in watts per square meter per decade. So that means the trend, how that changes. And then they show that comparing these models with the satellite data, then you see that there's an increase in outgoing long wave radiation, which here is as a negative value because more heat is leaving the system, which is so that's again this mainly from this Planck feedback, as you explained, Earth getting warmer, and the Earth radiating more heat to space. So if you just look at this, you would think the Earth would start to get colder, right? But that's not what's happening. Why? Because more sunlight is absorbed. And that's because less sunlight is reflected back to space. And that's really outside the range of all these models, where you see that there's much more sunlight is absorbed than what the models estimate based on the data, on the NASA satellite data. And that together cause an increase in how much heat accumulates in the Earth system. And that's again in the decadal trend, which I showed you already in this graph. And so I think it's quite surprising that Gavin mentioned that, while his own research shows, and I could show you the many other graphs where it's quite clear that the climate models don't show an increase in as much as of heat accumulation as the NASA satellite data shows. And that's really crucial, because that changes everything, right? That changes how fast the climate changes, which will cause how much impacts we will have, especially, again, in the Northern Hemisphere mid-latitude. And now one more point.
Was that because of the shipping change was the big reason for the discrepancy?
I think what they already mentioned in this paper is called series MIP, where they compare the MIP is relating to all these climate models, and the series is of course
measured data.
Where they start to compare the data from these climate models with the observations. And yes, one important indicator is indeed the aerosols, which also is mentioned that could be a reason of why we see much more sunlight being absorbed in the observations than in the models. But they've been waiting for the update of the emission changes until they started to do these model comparisons in more detail. But now this data is available, and it depends a bit on the resolution they want, whether they will start to work this out in more detail. But yeah, they are about to start to do that in more detail. I think there will be a lot more research coming out in the years ahead. But as I showed, the satellite data is only increasing further, right? So they will have to, the models will have to catch up. And whether that's based on the forcing agents or the feedbacks, again, that's the main discussion here, right? And I think we won't have time to delve into that, especially into the sunlight and the absorbed sunlight part of that now. But I just want to indeed go back to the Planck feedback, where you can see that looking at this temperature increase of about half a degree, then you can see that in over 20 years, then you can see that the outgoing long wave radiation from the Planck feedback, the effect, so how much heat is leaving the system, would be about 1.6 watts per square meter. And the math is pretty simple. Half half a degree multiplied by 3.2 is 1.6, right? And that's what the data here shows. In the blue line, Planck feedback multiplied by the temperature trend, change in temperature. And then here in red, you see the trend in outgoing long wave radiation from the satellites. So you see there is indeed heat leaving the Earth system, more heat leaving the Earth system in the infrared spectrum as heat radiation. As Dan explained, if the sun gets hot, it will start radiate more heat. If an iron in the fire is hot, it will start to radiate more heat, starts glowing red. But also the planet, if it heats up, will start to radiate about 3.2 watts per square meter more per degree Celsius of temperature increase. So we do see that now. More heat is leaving the system as it heats up rapidly. But there's a big difference between the blue line and the red line. And that difference is exactly the greenhouse gas forcing increase over the same period of time. Without it, that's the difference. Without these greenhouse gases, the outgoing long wave radiation would also be 1.6. And then that's quite, I think that's you at first you might think, oh, whoa, that makes sense, but in a way it doesn't make it's also quite surprising, because there's also the water vapor feedback, which would keep heat in, and there's also other, if you decrease aerosols and if you decrease clouds, that lets more heat radiate to space. So it's more complex than just this difference is explained by the greenhouse gas forcing. But I think it is quite interesting how this, how this explains it. It's 100 in a way. It explains it by 100%, but that does mean that's all of the story.
Okay. All right.
Yeah. So,
any other graphs there?
Yeah, I think it's.
I want to get to the what is the meaning, the importance of this study, or this thing that global warming is accelerating faster than we thought. And he said that one of the really important reasons why you should care about this is that obviously when things are getting warmer faster than we thought, that will lead to not only increases in more and stronger heat waves, droughts, floods, extreme weather in general, and those kinds of things, but also it means that the Greenland and Arctic ice will melt faster than we thought. And that means an influx of fresh water into the North Atlantic. And that is the thing that can shut down the AMOC, or the Atlantic Meridional Overturning Circulation, better sort of the ocean conveyor belt that brings warm water from the tropics up to sort of the Northern Europe region and keeps Northern Europe as being a nice place to live, rather than being like Northern Canada, which is where it's located. And it's not cold like Northern Canada because of the AMOC. And if the AMOC shuts down, which Jim mentions again, could happen in 20 or 30 years. And we've done a lot of programs on the AMOC, so check those out if you want to get into the details. But basically, if the AMOC shuts down, not only does Norway and Sweden and those places get really cold, but there's less water, there's less rainfall across the entire Northern Hemisphere. About a foot a year, by the way. We had Matthew England on a long time ago talking about this. And that's not good. But as Jim emphasizes, one of the big things that happened is that warm water that was going to the Northern Europe area no longer is flowing up there and is hanging around the Southern Ocean, hanging around Antarctica, and accelerating the melt from Antarctica. And he says we can therefore get several meters, or for Americans, greater than 10 feet of sea level rise in the next 50 to 150 years. And 10 feet of sea level rise, by the way, and it doesn't stop at 10 feet. It's just keeps going up from there. But but that amount of sea level rise can essentially wipe out most of the coastal cities, island nations, and things like that. And that obviously is a big deal. And it's not something, maybe the Netherlands can build a bigger dike or something, but most places won't be able to handle that. Places like Miami can't build dikes because the land is built on porous limestone, and therefore the water would just go underneath any sea barrier that you make. It just seep under, like it does today, by the way. They have flooding in Miami that just comes out of the ground because of all the porous nature of what it's built on. So why do we care? Because that means AMOC collapse happens sooner, faster, or higher probability, or whatever you want to put it. That's a big deal because it is irreversible on human timescale. I mean, maybe in hundreds or thousands of years it will reverse, but not in any time soon. And it's not like it makes everything bad, but it makes everything different. So wherever you thought was a good place to grow food, for example, because of the certain conditions and weather and rainfall patterns and things like that, out the window. If you really cared about, you don't like solar radiation management because it might mess up the Indian monsoon or the Amazon, well, AMOC will screw those up for sure and really mess with them. So these are the kinds of things that would happen. So this is not just theoretical discussion on, on climate science, the interesting news in climate science and some controversy. This is something that will affect you and your children, and certainly your children's children, I mean, for sure. And I mean, in any case, by the way, where we are with climate change. But if Hansen is right, then these things are happening faster and stronger than you've been told so far. I think Jim is right. He's been right all along. And I can't even understand why some of these mainstream climate scientists disagree with him without looking at the data and saying why they think the data is wrong. That to me is kind of mind-boggling.
No, they're not addressing the data. I think that's
Well, they're not. I mean, that's my point. They're not
that
addressing the
should,
data.
but it should be very, very clear to everyone. Those many of those who are objecting the findings are trying to build a narrative. They are often not objecting the data. If you look at the science, especially if you look at what the people who say we are exaggerating, they write that on Twitter or on Blue Sky or wherever they write it, their own research often shows that there is acceleration, the ocean heat content is increasing, the rate of ocean at a faster rate, and that aerosols are likely a contributing cause to that. But journalists are not asking those questions. Journalists are not saying,
They don't know.
this is what your science shows. Why are you telling this on Twitter, and why are you confusing people about what the science shows? Why are you saying NASA, NOAA, James Hansen are exaggerating things, while your own research shows now that we're not exaggerating things? They are not asking those questions because of, I don't know why, because I think people want, in a way, they want some hopeful message, or journalists like it to have like two camps, one saying one thing, one saying the other thing. But that's not what science is about. Science is about finding the truth, trying to understand what's happening in the real world, not about he said, she said bullshit, right? That's not what it's about. It's about trying to understand what's happening and how that will, and with regard to climate change, trying to understand what impact that will have on our lives and what we'll have to do about it, whether that is indeed rapid adaptation, of course, mitigation, reducing emissions, but also trying to make things from getting much worse. And that's really crucial.
And Jim wrote a paper long ago called Scientific Reticence, where he said that climate scientists have a sort of a built-in bias against too dramatic an outcome. And there was a basic reason for it. is that if you're an academic and you're going to publish a paper, you sort of have to be 95% sure that you're right, because the damage to your reputation of being wrong is much stronger than the damage to your reputation of not publishing
Yeah, but
something,
that's
right?
that's quite strange, right? You know what happens, like what kind of damage people are trying to do to the reputation of James Hansen because he just published scientific data, you know.
Right.
That
Well, yeah, I'm saying,
no,
but Jim wrote about this long ago. He said that the climate scientists are underestimating sea level rise. And the reason is, look, if I'm a climate scientist and I'm 95% sure that the sea level rise will be 3 feet or more, I'll publish that. If I think there's a 50% chance it could be 10 feet, well, I'm only 50% sure. So I can't publish that, even though as a citizen, I want to know if there's a 50% chance of sea level rise being 10 feet. That's incredibly risky, high probability, right? Incredible. But no, I'm sorry. We're only going to tell you, we're basically going to tell you the best case, right? We're not going to tell you the worst case, and we're not even going to tell you the mid case. We're just going to tell you that we're 95% sure that the sea level will be 3 feet or more, but that's all we're going to tell you, because that's, 95% sure. So anyway, it's not a good way to do it. You'd never win a war if you worked with your data like that, right? We're 95% sure that the enemy is this many soldiers or more, instead of looking at what the real numbers might be. So anyway, I think we should, by the way, unless you have something else, I'd like to move on to questions and
yeah,
then make it to be an interactive thing. And maybe we can bring in Stacy and see what kind of questions we had on YouTube. And if you have questions on Zoom, then post them, and we'll also take a peek at Clubhouse. If you're on Clubhouse, post them in the chat and we'll take a look at those. Welcome, Stacy.
hi Stacy.
Thanks. Hey, Dan. Hey, Leon. And welcome to the family. It's so nice to have you on board.
Likewise. Thank you.
Yeah. So there were some questions. I wanted to just call out some chatter that I found interesting. Well, first of all, the ones who were trying to throw down about who drives less and their bikes and stuff. I was very appreciative of that. And there were some wondering what country we should say we belong to or whatever. And somebody wisely said, I think it was Jean, that we we are all citizens of Earth, although we don't behave as such. And it's, another point that the climate doesn't care where it comes from. It's like we're all doing it. We're all contributing. But of course, some are more to blame than others. Yeah. And then the one thing that I saw in the Hansen memo that I'll just read is this is a time as the world focuses on cultural and shooting wars to gain the scientific understanding needed to address climate change, if and when the world comes to its senses. To increase the chance of success, it is important to maintain and initiate crucial Earth observations. Among these are continuation of precise global measurements of Earth's radiation budget and expansion of Argo autonomous float measurements, undersea ice and ice shelves, which brings me to my question is, do you guys know the latest on what's going to continue or what's not in terms of NOAA, NASA, etc.?
Yeah, I think that. Thank you for highlighting again that important last paragraph of what Jim wrote. I think that's indeed a very important aspect and we really need more of these satellite observations, and also indeed the ocean heat content data. And I think surprising, let me just give you a few examples, of course, on what the new presidency is doing as far as like the worst things I've seen, let's say. One is when I was visiting this coal-fired power plant in the north of the Netherlands, we also visited a location where they were starting for these ship out the bases of these enormous windmills, these 15 megawatt wind power wind turbines, and they were also this RWE is the second largest global producer of wind power, offshore wind power. And they said they had the one project off the coast of New York, and they said, okay, we'll just have to wait 3.5 years because we need a signature from the president, and he will not give it to us, right? So that's and one other thing I heard was that it says 6,000 or 8,000 of these electric vehicle charging systems at the government buildings are about to be shut off because Trump wants them to or something. I don't. I think it's quite surprising if you have if I don't know exactly what to believe with all this media, but it seems like Elon Musk has quite a strong bond with the president. He has of course, he has an electric vehicle company. So it's quite surprising that they are shutting down these charging stations at all these government offices. But I don't know.
But the oil companies gave him many, many, many millions of dollars for his campaign, and he said, "If you do that, I'm going to help you out." And he seems to be keeping his word on that, at least.
Quite strange.
Yeah, I think. By the way, on this particular thing, of course, the more serious things that could, first of all, obviously, the United States is going to suffer in its scientific leadership in the world. There's no question about that. We're shutting down all kinds of research, not just climate research, like all research. NSF funding, which is what funds professors doing research in universities across the country. And he's shutting that stuff down for now, or at least trying to interfere with it. This is causing all universities to scramble to figure out even how to stay open. And he could screw it up. By the way, people have optimism bias. You can fuck things up, and they will be fucked up. So he could try that, and he's certainly going to fuck up a lot of things, including, obviously, America's leadership in the world. He's trying that as quickly as he can do. The USAID, people think of it, oh, why are we giving money to these other countries? We do it for strategic reasons. We want to have exports from those countries of whatever they have, and this is one way we do it. China, it's called Belt and Road Initiative. They ramped up their aid around the world in order to have more access to the world. We also want to, these USAID programs are there to minimize terrorism and violence and things that are going to get us. That's why we do them. We're not just doing them because we're good people and want to help the poor or whatever. We do it because
we are not.
They're strategic. So these things are going to all messed up. But I think the good news about what Jim is
a reason for that.
Well, there's reasons. I mean, but I think that when it comes to Earth observation, obviously the big risk is that the NASA approach to monitoring these things will get shut off, and I wouldn't be surprised at all if that happens. The good news is Europe could do it, China could do it, and China, by the way, is really ramping up climate science. When you see these papers come out, there's a whole lot of Chinese authors on these papers, and they're ramping up their space program, and even private individuals using these microsatellites. I mean, I worked on satellites long ago. You could never get away with that back then, but nowadays you could fund a satellite for a few $1 million. Especially some of these that are just doing kind of very precise measurements of something, not doing a lot of other things. They could use a microsat for that. And so I think that these things will probably be done, but that's a very risky thing, is that we're going to be flying more blind than we certainly needed to be because of the reaction to Trump. And by the way, there's a million other impacts it's going to have on the economy and just, government. Government is there to help society function smoothly. You get rid of it, you get rid of half the people, you think you save money, but you didn't save any money because you're just going to make the whole economy run that much more inefficient. The one I give an example to, let's say I'm here in New York right now, visiting my daughter, and let's just say they wanted to save some money, so they shut down the subways. Okay, the government would save some money. New York would just come to a stop, and businesses, I mean, nothing would happen, right? People couldn't get anywhere. You couldn't go shopping anymore. You couldn't get to work. Cars would jam immediately and nothing would move. So yeah, saves money. I mean, the very first thought, you're going to save money, but it's insane to do it. And that's exactly what we're going to do. We're about to see what it is, what happens when you do stupid, insane things.
Well, I would say, yes, I mean, I'm all for transit, but
So,
New York is also a compact, densely populated place, and I would say start riding a bike.
by the way, well, that bicycle thing right outside this apartment. Uh, but Stacy, for you, I don't know if you heard this one. Half of all mass transit rides in the United States are the New York City subway. New York City subway is half of all mass transit in the entire United
Frankly,
States.
I would have guessed more because
Well, it's big. I mean,
there
obviously it's
is
huge.
such a chasm between New York's transit and any other place.
Okay.
Chicago does an admirable job. We do some here, but it's so disjointed in the Bay Area. I mean, we're
Okay.
minuscule, and yet we have like 29 transit agencies in the Bay Area. It's just nonsense.
Let's get, I want to end by 3.
Oh,
So
I have lots of
so
questions on here.
yeah, go.
Well, one follow up to what I had mentioned or from Hansen is, should we be crowdsourcing more Argo floats? Like, how much do they cost?
That's a good question.
Yeah, I think that's so indeed we need more Argo floats, and I don't know what one Argo float costs, and I think that's a you do need a program. So it's not something you can like have everyone just throw a Argo float out into the ocean. You really want this to be well managed, and to have the systems at the right place, and as Jim mentioned, at the locations where we lack the data, which is of closer in the Arctic and in at a lower depth ocean. So if that should be professionally managed, and I think that's why we have these government systems in place, right, to make sure that this is done well. But I think I don't know, but maybe a private party could, of course, assist in especially with these NASA series satellite data. NASA has developed these lower cost, smaller satellites, and I think that is there are more companies out there which have satellites which they use for observation systems, where they have or for weather satellites. So there are more and more private parties getting involved in more and more fields with satellite, because it's becoming more and more affordable. And I think we are reaching now a point, whether it's NASA or whether it's NASA partnering with whether it's other space agencies or with other satellite agencies, to get more reliable, that's also to secure security, that we do have, to make sure that we do have data in the years when maybe one point failure problems occur, that we have a backup satellite, but also to increase accuracy, to have more passovers at different times of the day around the world. I don't know exactly what would be the right setup for that, and I think that's, again, we should work with that with NASA. But I just suppose, if we would have 10 satellites, of course, we could have maybe twice or 3 times as better a better accuracy of the data, so decrease the uncertainty range. So I think that's I think, and yeah, maybe
What's
we
the
should
status of
Well,
the aerosol satellite, though? There was the one that was actually launched, and isn't it on station now and starting to collect data? The aerosol, I don't remember what it's called, but I thought finally there was an aerosol satellite that was launched.
There's Earth Care, there's different satellites, and they're now starting to come online. So indeed there's what's called the Glory mission, or was that the old one? I think there's the other satellite from NASA that has come that has been launched last year, and there's a methane satellite. There's more and more satellites being launched, and of course it takes a while for those to start up and for data to be
So the
accumulated.
calibration.
and then starting to visualize this data and to do research with it. It takes a while, but we're starting to get somewhere, and other satellites are starting to go offline. So it's always, yeah. But I think that just looking at without looking at the politics, that might be one of the few benefits of Elon Musk partnering with Trump. They'll I don't know, just
well, no, Elon wants it all to be private. He doesn't want NASA to do stuff,
No, I mean that satellites that will be cheaper to launch satellites.
Oh yeah, SpaceX makes it cheap to launch. As I said, other countries are ramping up. China and the EU can do it as well. But
Planet Labs is one that has
been around for a long time.
Is doing global monitoring.
And there's a lot of new things happening. There's synthetic aperture radar satellites, which Planet Labs does visual. Basically, it's mapping the Earth every day.
Yep.
Using visual satellites for Planet Labs. There's another company doing synthetic aperture radar every day. So, there's a lot happening in the Earth observation area. But some of these are specialized, like looking at aerosols and energy imbalance. These are special science satellites, not the ones like that. Maybe you can get stuff from Planet Labs, which are doing it for commercial reasons. I don't know. What are some of the other questions? Or let's bring Eli in as well.
Just to cap that off, I should have been able to answer the question with gotta call Saul. So I'm sure he would know how much Argo floats cost. Saul Griffith.
Maybe.
Yeah, he's working on something like that. Okay,
yeah,
Nadia
Carina von Schuckmann can also answer that. But
who? I'm sorry, who?
Carina von Schuckmann. She's in France, I think still.
Okay.
She's a colleague.
Nadia had some questions. What'll be the effect of the greenhouse effect on wind and waves in polar regions? Living on boats in the Arctic might have trouble with wind and waves versus they're saying temperature differences are small. But
anyway. In general, I think one thing you should take a read. It's a long time ago, but the book "Storms of Our Grandchildren" by Jim Hansen. The title is all about how, as the world warms up and you get a lot of icebergs coming off of Greenland, that causes like an immediate cooling. So what's happening now is the Arctic's warming faster than the rest of the world. So the temperature difference between the North Pole and the equator is dropping because the equator's warming up, but not as fast as the North Pole. So the difference is going down. And that's making the jet stream wavy and giving us all the crazy weather and the cold snaps in Texas, which is Arctic air comes down that floor. Then you got a heat wave because of the warm air goes up north. So all that's happening. But then when the icebergs happen and the AMOC shuts down, when the AMOC shuts down, all of a sudden it gets much colder up there. And now all of a sudden you have a huge temperature differential, which drives storms like we've never seen before. Those are the storms of our grandchildren. So the longer term prognosis for storminess is out of sight. I literally, and Jim and I don't know how, this is right or not, but showed these boulders sitting in like the Bahamas. Like, how did you get this boulder on the land? It's huge. And he said, before there were storms that were so strong that could throw this 20-ton boulder onto the land. And we don't have those anymore, but we could have them again if we screw around with the AMOC and all of these things. So yeah, that's a quick answer.
And there's a lot of energy in these. There can be a lot of energies in these superstorms, and I think that the AMOC is important there indeed, where you can see, as Jim explained it, that the amount of heat transported by the AMOC, it's a 1 petawatt is a one with 15 zeros joules per second of heat being transported through the Atlantic Ocean northward from the southern hemisphere to the northern hemisphere, and that's equal, as Jim explained it, as a doubling of greenhouse gases for one hemisphere, so 4 watts per square meter over the entire hemisphere. So that's less heat being, so if it would shut down, that's less heat being transported northward. But that would stay in the south. And that's such an enormous amount of heat. It's hard to grasp. If you look at it, I think it's 20 zetajoules. And if you would have that heat to melt land ice, every year you would have 25 centimeters of sea level rise. So just, of course, that's hypothetical, but just to give you an impression of how much heat that is, 25 centimeters of sea level rise for every year of heat that's would be transported northward, right? So if that would stay in the south, indeed, that's a big risk that it could start melting more more ice around Antarctica and on Antarctica on land.
She also asked, are there models predicting casualties from climate or system models that try to capture the feedbacks between population and climate?
Well, by the way, one thing to do is to take a look at our recent program with David Keith on whether solar radiation management will kill more people than not doing solar radiation management. And that particular study does have a model for how many people die from heat exposure, but that's only heat exposure. So it was, and the answer, by the way, the quick answer was 400,000 people a year more die if you don't do 400,000 people more die every year if you don't do solar radiation management versus if you do it. That's the delta. But that was very conservative. It didn't include AMOC shutting down and didn't include famine from heat waves. It didn't include any of that. It was just the heat exposure. So there are some models, but I'll be honest with you, I don't think climate scientists spend much time working on that, on the climate feedback to deaths. I mean, there's probably other
especially
groups, maybe military
regional
groups.
impacts.
Say again?
Yeah, especially if you start looking at what are the real regional impacts, as I mentioned, for example, from India, with continued greenhouse gas emissions and rapidly desulfurizing its coal plants, as it's planning to do, as we discussed before, and there's almost no research on these kind of things. We see it now. We see it now happening in Europe already, where we have 50 or 60,000 heat deaths almost every year, because we have such a rapid warming, and it will get much worse. Yeah, we are now on May 1st, the shipping industry will start decreasing sulfur emissions over the Mediterranean, especially in the region, of course, where we have a lot of heat deaths already. Spain, France, Italy, the Balkans. Those will be impacted a lot.
So Eli, before we get going here, maybe we'll have another few questions from YouTube. But Eli, do you have a question or a comment?
So yeah, refining my question from last week because I wasn't clear enough. I asked about tail risks, but really the key question and our exchange when you had the graph up kind of is a good setup for this. The tail risks that I am most concerned about are if the uncertainties in especially the amplifying feedbacks, but also if on the minimum side, the uncertainties on the negative feedbacks, the damping feedbacks are wrong. That can put us in a worse situation, and not only that, that can put us in a worse situation earlier than we expect. And of course, if that's the case, then all of the projections further out from that are just totally off, right? So the risks of not of things getting worse faster, I think, are like really not grappled with sufficiently. And I'm wondering if you had any thoughts on that.
Well, of course, that is, I mean, to be clear, this is what Jim is saying, that because ECS is higher than was assumed, that things will, this is what he's saying, They will get worse faster than folks thought. And we're seeing it right now. It's not like some future thing. We're seeing it. He's saying 2025, actually, he said might be a record temperature, which would be mind blowing after the El Nino goes away. So, and if that happens, it's all really, I don't know how anyone would argue it's not the ship emissions doing that. But anyway, Leon, your thoughts?
So that's water vapor. I think I just read it. There's just a paper was published, I think last week, where they show that because there was a decrease in winds, which decreased evaporation, which of course decreases water vapor. So that might, I think that was an important point, that the Planck feedback and the greenhouse, the difference between observed outgoing long radiation and the Planck feedback was explained only by greenhouse gases. And then you can wonder, like, what happened to the water vapor feedback? Because it's a strong amplifying feedback, which would have caused more heat to a decrease in outgoing long-wave radiation also. But yeah, and I mentioned maybe some decrease in clouds also increase outgoing long-wave radiation. But it might also be that without that, if the winds pick back up, you're right. If these winds start blowing more, then we could see more evaporation, more rain also, but also an increase in the water vapor feedback. And then I think this is really answering Eli's question. So if the impact of clouds is strong, so George already talked to you about that. Or that it's likely does show, the data shows that the cloud feedback is stronger. The amplifying cloud feedback is stronger. So more warming causes a decrease in cloud cover, which causes an increase in how much sunlight is absorbed, causing more warming. So that I think that's, yeah. I think more and more data points to the climate sensitivity. The climate being more sensitive to greenhouse gases and also aerosols. If you reduce aerosols, the climate impacts will be higher because because the amplifying feedbacks are stronger than most thought.
I think, by the way, I would add, I think the tail risks are not, I mean, like, I think Jim is right about what the climate sensitivity is. I think the tail risks come from society, that people think that somehow we have a robust, functioning civilization. But as we found out in 2008, you can pull a little card out of the house of cards called subprime mortgages, something no one ever even heard about before. And that caused all this kind of havoc. And that was one little thing in the overall system. And now we're going to be pulling cards right and left out of the deck and out of the house of cards. And there's nothing that says this complex system will function well when that happens. And we're about to find out, because forget climate change. We're just screwing with the system right away without even the climate impacts that are layered on top, of course. So anyway, we'll find out about that.
Yeah, I mean, the other point that I want to emphasize is that, what we're projecting on each of the amplifying feedbacks is kind of based on what we're expecting the temperature to be. And if we get out of the band that we expected, then we have to revise the feedbacks that would be expected at a particular time. Right. And
permafrost melt and cloud rates.
So the point is, if we knock over the first domino, then all the bets are off. And I don't think that people have really grappled with that, other than doomers.
So Stacy, we're over 3. I want to end it, but is there another question or so from YouTube that we should address?
Yeah. One that I think is funny and ties into this whole, you said doomer, and it's like, someone asked if there is a polymarket bet for Hansen's 2025 predictions, And I looked, and the only climate bets there are on Polymarket are February 2025 temperature increase, 2025 February hottest on record, and will 2025 be the hottest on record? And they have about $1.7 million in bets on those. But of course, they will run to the end of the month or the end of the year, and they'll be replaced by ones later. So there's not one specifically on Hansen. But if you are
that
interested,
2025, if it is the hottest ever, 2025, that supports Hansen. So that in some sense is what he didn't predict.
Yeah,
that.
True,
He said
true.
it could be the hottest ever, which again is mind blowing if it is. So that would be it.
So what are the odds there? Do you know?
What's the odds on 2025 being the? By the way, I think February is dropping a bit.
It's a 25. Whoa! It's a 25% chance, and that is down from the high of New Year's Eve and January 31st. It was
again, all it has to be is roughly the same as 2023 and 2024 for Hansen to be right.
Right.
If it's a record. Again, I don't even know how anyone else could possibly explain that, but it might be a record. We'll find out. We'll have a better understanding in a few months. Even
I was just going to direct anyone interested on betting on the climate to our friend Elliot Jacobson's site, climatecasino.net, where you can place bets.
Okay. All right. So anyway, I think first of all, let me summarize. First, because I always forget to do this. Everyone out there, please like, subscribe, follow, because what we're trying to do is reach a lot of people with this important climate information. You can do your part by helping the algorithm spread this to more people. And the simplest thing is just hit subscribe, hit like, and hit follow on YouTube or on Blue Sky. I'm sorry, Twitter, X, and Blue Sky. So please do that. Again, I want to welcome Leon. For those who didn't hear the original announcement, Leon is joining the Climate Chat team. He's going to have his own programs that he'll run at different times than Sunday morning at 10 o'clock. I will join him sometimes on those. We have one scheduled probably for March 17th, but we'll refine that a little bit, and maybe there'll be some others. And it's going to be great. It's already been great having him on as a frequent guest. And now running his own programs, we're going to be increasing the content on Climate Chat. And what you'll hear about in the coming weeks and months is how we're upgrading the technology to improve like the visual quality and these kind of things, as well as adding features like YouTube memberships and Patreon so that you can help support the growth of the channel yourself directly. And again, help spread the word out, because this is really some of the most important information out there. And to be honest with you, I'm really surprised that it's not covered much by obviously mainstream media, but even by other climate channels. So we're trying to do our part, and we're going to be able to do more with Leon on board. So a big welcome to Leon Simons, and thanks for all you've done in terms of climate science, helping Jim with his paper, your own research, and also communicating it to the public through what you've done on social media and what you've done with helping us out here on Climate Chat. So a big welcome. So thanks, everyone. And so we will see you next time. Next week's guest is David Fenton, returning guest, talking about climate communications, critical thing. We'll have an update probably maybe by then on when we're doing the Jim Hansen interview, which won't be a live interview, by the way. We're doing a special thing with Jim to make a very understandable, very information-dense interview that could be broken up into pieces to get important points out to the public. So we're going to try something a little different that I think is going to be really cool. And anyway, so we'll give you more on that as it comes up. And thanks, everyone. Thanks, Stacy. Thanks, Eli. Thanks, everyone out there. And we will see you next time.